This is video help for the fourth problem of homework due tomorrow. The fourth problem has these 9 multiple choice things, and let's see how many of them we can get right. It'll be really fun to see if we can really get them. And to help you focus on that without divulging too much, let me try to say 9 things. For problem 1, it's cute that you could, of course, just write some equations and solve for when they collide for some arbitrary velocity. For a multiple choice question like this, can we answer it just by considering the limit? Consider a limit, for example, where the second ball, you're throwing it straight down and they haven't said what velocity, and therefore think of a very large velocity. Problem 2. Remember the monkey, shooting the monkey in the tree? This is like that, where I'm, throwing and aiming, a ball straight at, another ball. And the question that you should do is check and see, is this the same thing as the monkey situation? Are the initial conditions here and the way this is set up, is it exactly the same as the monkey thing? Problem 3. Let's just get some conventions, some of our questions of how we're going to write down diagrams clear, how we will make them consistent. Suppose I call A the acceleration. Let's suppose this guy is accelerating downward. Then what I would do, if A is a positive number, I draw A like this. And you'll see if I drew my arrow the other way, I'd have to put minus A. So A is a positive number. That means that if I write this acceleration here, up is going to be the same as that down. If I write an arrow up, then I put A next to it. If I drew this arrow down, I would put minus A. Another thing, if I define alpha this way, I will know that alpha is positive, because A is positive. If I drew it the other way, I would have to, whatever alpha I had, I could call that alpha again, but that will come out to be a negative number. And with these conventions, being careful with those conventions, it will help you as you think about this problem. Problem 4, a couple of things. When we're talking about a person pulling, imagine we're talking about the hand as a system, and there's tension up, pull on it from the rope, and he's pulling down with his arm muscle. And so with the hand mass being negligible, the force that he's pulling down is equal to T. So that's step 1. Step 2, you can think about, to get a quick overall assessment, you can just treat this as a system. You got external forces of gravity, and then you've got how many contact forces here? Finally, this thing is being pulled up at a steady rate, no acceleration. Therefore, even if these masses are non-zero for the pulley, even if they have some non-zero moment of inertia, the tension around any pulley, the tensions on both sides will be equal if they are not being accelerated, if there's not an acceleration in the system, so that this eats up part of the tension. So even with mass here, T will equal T prime. So we do not have, in this case here, different tensions in the rope. In problem 5, I've got a tiny putty ball coming and hitting a bowling ball. Afterwards, the putty ball sticks to the bowling ball, so the velocity at the end is common to both. Problem 6. When I have a collision like this, and it'd be true up here too, when I have a collision like this, do you remember that when we collide, the impulse that this golf ball in this case feels is exactly the same as the impulse that the bowling ball feels. Look up what impulse is. Number 7, the ant has a huge mass. So, it's got some huge mass. It's much bigger than the board. So as the ant walks, by the way, what's the board going to have to do? Problem 8. You've got angular momentum. You can characterize it as I omega for the figure skater, and her kinetic energy as 1/2 I omega squared. Which of these is conserved? When she pulls in her arms, what would happen to the moment of inertia? What would happen to omega then? Number 9. A straightforward way is to remember our harmonic motion as x equals a cosine omega t plus phi, and therefore v is minus omega a sine omega t plus phi. And therefore omega a is the maximum value of the velocity. And omega is the square root of your effective, spring constant over your mass. So you can go ahead and, make a little list of, what is your omega for this, for these cases, what is A for these. This, by the way, is each of these is compressed away from the origin here. So this is compressed in 2 units and then released from rest and so forth. And by the way, this all would be consistent with the fact that 1/2 kx squared plus 1/2 mv squared equals constant. Therefore, when this is 0, this is maximum. When this is 0, that's maximum. And in fact, then they're both equal. So that constant and equal to each other. That is 1/2 kx squared maximum is 1/2 mv squared maximum. And so if you think this way, you'll get the same, formula that you've got there for the maximum v. So let's try to get them all right. All right, thanks. Bye.